And the specification, okay, let me write that down. Okay, K tilde as it stands is not, or let's say, does not give rise to a well-defined propagator, as K tilde has a pole at E equal to curly epsilon equal to E. Okay, so sorry, this is epsilon, or this is E, yeah. So we need to specify the contour and in doing so, we shall see that we implicitly have to specify the temporal boundary conditions or condition. Okay, so this is a bit mysterious sounding statement, but let me tell you what I mean. So let's write down the formal solution. So the formal solution we found is K x of t, x prime t prime is equal to 1 over 2 pi h bar to the power 4 or something, d of e d cubed of p, e to the power minus I epsilon t minus t0 by h bar plus I p dot x minus x prime by h bar, and I should call this t prime, not t0. That whole thing divided by e minus epsilon minus e. Now, let's look at one solution, which I'm going to call the retarded or the causal propagator. So the causal propagator, so when t is greater than t naught, then what happens? This thing is positive, right? Now, if I look at the epsilon integral, so I think of epsilon as a complex quantity. We have to, otherwise, our integral will be not ill-defined. So this is the epsilon plane. And on this plane, depending on what the value of E is, there will be a pole here. It could be here as well. But let me just take that to be on this side. So now the thing is that the contour, the integral is going to go in this direction, the E integral, epsilon integral. But when it comes to the pole, it hits a snag. So we will have to go either below or above. And then we have to keep on doing the integral. And when we go below or above, this guy will have some small radius r. It could also be above r. And after the integral, we take r to 0. So it's like a mouse hole integral. But since we're going to do a contour integral, we have to close the contour. Now we can close the contour in two ways. We can either go above in the lower half plane, or we could go on the upper half plane. So now t is greater than t naught, and this is my integrand. Can you tell me, should I go on the upper half plane or the lower half plane? And then after the integral, we'll have to take the radius of this half circle to infinity. So can someone tell me if I should go on the upper half plane or the lower half plane? Remember that t is greater than t0. Sorry, not t0, let me call it t prime. Can someone tell me?
From the below.
Right, because this is positive, and if I go in the lower half plane, then epsilon is going to be, its imaginary part will be negative. So I'll get a minus I times a positive real quantity. So minus I and minus I gives me a minus sign. So when I take r to infinity, the contribution from this guy goes to 0, right? Whereas if I took this contour, the contribution from this guy would blow up. So for t greater than t0, Shujosh guessed right. The contour that we have to take has to be on the lower half plane. But we want that propagator to not vanish. We want the effect to propagate in the future. That means that we have to take in the contribution from this pole into account. That means that we should take the mouse hole part of our contour in this direction so that the residue due to this pole is included in the contour integral. Okay? So this is t greater than t prime. But if t is less than t prime, let me copy and paste this so we don't have to. So in that case, what do we have to do? What should we do? Should we do lower half plane or upper half plane? Now, see that this thing is negative. Shujosh?
Yes, I think I haven't thought about it much, but from the above, would feel like
yeah, it should just go on. It should be the opposite of this, right? Because now that E is the imaginary part of E is positive. So if I go on the upper half plane, on the upper half plane, and close the contour, and when I take the radius to go to infinity, that's when this is going to die off exponentially. But we want this propagator to go to zero, to be zero, because otherwise the disturbance is going to propagate into the past, and therefore the small contour will still be the same, the mouse hole contour. Okay.
So why is it a problem if it propagates to the past?
Why is it a problem if it propagates to? It's just not the causal propagator, right? I mean, it's something that you could have done something in the past, and for example, you could have set up the whole system sometime in the past, right? So if your thing is propagating sometime in the past, it's not accurately portraying that. Okay, so I mean, you can do that, and that's also a valid solution, but it's a, it's it's not the solution that we are looking for here. That will also be a valid solution, okay?
Oh, okay.
So if I do this, then combining these two things, what I've done is that t greater than t0, the k tilde p, let's call it retarded, and this is not a politically, this is not a pejorative term or anything. We can also think of it as pushing the pole slightly in, in the positive upper half plane. So this is same as this times 1 by epsilon minus p squared by 2m plus v of x plus I omega. Because if I push this slightly, hang on, yeah. Actually, this should be a minus sign, I think, yeah. So, because if I push this slightly in this direction, then I can take the contour along the x-axis. And then afterwards, I push it back. Okay? Similarly here, if I push this down slightly, then I could take the contour like this, and then I can push it back. So this little imaginary distance is called omega. Okay? And that's what we are putting here. But afterwards, we are taking omega to 0. So our solution is that k is this thing when t is greater than t0, but when t is less than t0, let me, k tilde is just 0. Okay. Now, there is another choice, which is called the advanced propagator. In the advanced propagator, if you have t greater than t0, then you have this guy going like that, and hang on, sorry, the contour in that case is, so this is my pole, and the contour in that case is, it goes like that, and it goes like that, and this goes like this, and it goes like this. So that, this is going to be a 0, so therefore, the disturbance is not going to propagate into the future, and t greater than, and if t is less than t naught, then we will have this thing, and this thing, this, and then in that case, disturbance will propagate into the past. And now I've been thinking, and let's come to Nahi's question: why did we have to do this? And we could have just we could have done something in which disturbance could have propagated both into the future and the past, right? And in quantum field theory, in relativistic physics, so in relativistic physics, we do have that. We do have that. But it has an interpretation that disturbances propagating into the past are antiparticles, okay? But that's going to put us a little bit beyond the scope of this lecture. So, this thing is called the advanced propagator. And you can have all kinds of different boundary conditions depending on what problem you're trying to solve. Here we are trying to solve a very specific problem, okay? So I think this is so I wanted to show you how choosing the contour integral gives rise to a boundary condition in time. There's something in the propagator. I think this is something very useful. Now what you can do is that, we can now explicitly evaluate the propagator. We can explicitly do the E integral, epsilon integral, which is just a contour integral, right? So then when t is greater than t is 0, all we have to do is we have to just, we have to use Cauchy's residue theorem, right? Do you want me to do that explicitly? Let me do that, okay. So what was our integral? Our integral, we are doing the dE integral. So we have, according to the Cauchy's integral theorem, so we have k xt k prime t prime, then limit is epsilon goes to E, and then will be 2 pi I, and then there'll be an epsilon minus E. We are not doing the dp integral, so there's going to be dp cubed by 2 pi h bar 4. And then in the integrand, we're going to have E minus E, and then here we will have e to the power minus I by h bar epsilon t minus t prime plus I h bar p dot x minus x prime, right? So so this thing will cancel this thing, and so limit epsilon goes to E. So what we will have is that, and then the 2 pi will cancel this 2 pi. So I'm missing a factor of h bar, but I'm not going to bother about that. So we'll have d cubed of p 2 pi h bar cubed or something, and then we'll have a factor of I coming from here. So we will have I, and then we'll have e to the power minus I. This E is now the energy of the particle, the on-shell energy, and then we will have plus I by h bar p x minus x prime, okay? So this is when t is greater than t naught. When t is less than t naught, this whole thing is 0. So therefore, we can write k for any t, x t, sorry, t prime, I keep on using t naught, t prime. So for any t, x prime t prime, we will have integral of d cubed p by 2 pi h bar cubed I E minus I, the energy T minus T prime plus I P dot X minus X prime times a theta function which says T minus T minus T prime. Okay. And now you can just verify that this theta gives rise to a delta function in time, and all that nice kind of stuff. Okay.
Sure. Did you use theta to make the fact that it doesn't propagate into the past?
Yeah, exactly.
But like, so where did it came from? Like, do we supposed to put it manually?
This result for all t, for arbitrary tree. For arbitrary.
Oh, okay, yeah.
Yeah. So that this is 0 when t is less than t prime, but it's 1 when t is greater than t prime. Okay. And this is the expression for the propagator. Okay, I think I'm going to end here, but are there any questions? The last bit is too much, I think, but not too much. I mean, I think it's interesting. This is something you should have seen something like this in electrodynamics when you solve wave equation with the source, but not many people do that.
We didn't in our course.
Okay. Yeah, we weren't shown the stuff.
So from Maxwell's equation, you can derive, this is the D'Alembert of a mu x of t is equal to delta for x minus x, x prime. And so this is a wave equation with source. And this is the wave equation. You can show. But if you have a source, what you can do is that the idea is something like this. Suppose you have a linear differential equation, okay? So phi is the solution. So this is your linear differential equation. So this is your source. So in general, we have, say, in Maxwell's equation, we have current, we have charge, right? Those are the sources. Now, the propagator K is the inverse of the linear operator. And that's exactly what that equation is saying, right? That the Schrodinger operator acting on the propagator here, the Schrodinger operator acting on the propagator gives you the identity. That's exactly the definition of a propagator. The definition of the propagator is that it's the inverse of the linear wave operator. Okay, so suppose you have solved this, so you know what K is, and suppose you have another solution, which is the homogeneous solution. Then the general solution to this equation is given by, there might be a phi naught plus K times psi. So K is telling you how to propagate a unit of disturbance. And psi is the weighing factor. So now if I apply L to phi, I get L phi naught plus LK psi. So this term is 0. And then the second term is give me the identity psi, which is exactly, so as a result, we get exactly this equation. So to find the propagator in electrodynamics, we have to solve this equation. Okay? And this is what's telling us that, there is a wave propagating at the speed of light. And that's where, we have to make a choice about whether your disturbance is propagating forward in time or backward in time, okay? And you want to choose the retarded propagator because you want to understand how things evolve in the future, whereas the one backward in time is more of a mathematical, curiosity. But in quantum mechanics, the propagator, in relativistic quantum mechanics, the propagation backward in time has a physical interpretation as an antiparticle. But that's beyond this course. Okay, any more questions?